No, first I'm going to give you the algorithm that we informally gave an example for. And once we have the algorithm stated, then we'll go through the example one more time, this time paying more attention to certain details. And then we'll have an example proof which gives insights. Then we'll have a general proof which actually does the job. So the algorithm cover is used for solving the tree network covering problem that I stated before. The input for the algorithm is the tree network described by, say, two lists, one stating the vertices, the other one stating the neighbors of the vertices. The vertex set, the edge lengths, and the numbers. I'm going to prefer to use, well, let me use them as R1 up to Rn. To solve the problem of minimizing the cardinality of the set X subject to each closest distance to each vertex is less than or equal to some number Ri, and X is to be chosen from the tree. And we call this Q of R, the minimum number, to be the minimum, to be this way. And the RIs, well, I was trying to avoid the use of RIs because I didn't want you to confuse them with the RP, which is the P-center optimum solution value. But let's not worry about that because I'm just used to that notation, and I'm afraid I may make a mistake if I switch notation right now, okay? Because it's sort of ingrained in my mind for many years, and let's just stick to it. RI, in the context of P-center, will become this number, where R is a parameter, fixed parameter for the covering problem, but actually it doesn't have to be related or defined in this particular way. Ri are just non-negative numbers which define the radius of each vertex Vi to a closest element of the point set you're looking for. So to solve this, you input that, and initially, step 0, we initialize as follows. The green tree is denoted by G, and that's the entire tree for the beginning. The iteration index is 0. There's a certain set, which is U, and it will depend on the iteration index. So U0 at the beginning is empty. And the brown tree is denoted in my notation by B. At the beginning, the brown tree is a singleton for each tip vertex Vj. For non-tip vertices, you don't have any brown tree. Okay, so the brown trees are just really single points at the beginning. To initialize, we fasten a string of length Rj at each vertex Vj. And let me define the capital J to be the set of indices 1 up to n. Okay? So that's the initialization. And now we continue with steps 1, 2, 3, etc. The first step is to choose a tip vertex T of G. This is going to be some vertex it's one of the tip vertices of the current green tree. So as you go along, something which is not a tip vertex at the beginning may become a tip vertex later on, okay? Because you keep updating G. Actually, you keep shrinking it or trimming it as you go along. All right, so when you make that choice, if the green tree consists of only of that particular vertex, then you're done, essentially. If this is the situation and there are no strings at the chosen tip, we go to the termination step, which is step 7. If G is T and there are strings at the vertex T, we again go to a termination step, but we have to do a little bit further processing, and that's step 6. If neither is the situation, we go to step 2. But prior to that, we find the vertex AT, which is the unique vertex adjacent to T in the green tree. Okay? Tip vertices are adjacent to exactly one vertices, and so AT is the unique vertex in the green tree, which is adjacent or neighboring to T. Step 2. If no strings attached at T, we color the portion of the edge between T and its adjacent vertex AT brown. And we go back to step number 1 because the green tree is updated now. Okay? Otherwise, we go to step 3. In step 3, you pull all strings tight towards AT. Pull tight means, of course, you actually make them coinciding with the edge segment under consideration. Yes?
What does the second line of item if G is T and strings
Are you referring to that? If G equals T, this one? If G equals T and there are no strings at vertex T, go to 6.
First one is
No. The first one is no strings. The second one is there are strings. Did I say no strings? Well, I meant there are strings. Well, in the first case, there are no strings. In the second case, there are strings. I just omitted the word there are because it's just too many words. All right. So pull all strings at T tight towards AT. If all these strings reach AT, we engage them at AT. Engage means you just, whatever the portion of the string is you just engage it, and there are loose ends still remaining. Okay? Color the edge portion TAT brown again. And go to 1. If not all reach, you go to step 4. In step 4, well, what happens is you've pulled all strings tight towards AT, but at least one string did not reach, which means that you're going to have to locate a center now, some facility at wherever the shortest string that was pulled tight and did not reach. That point determines a particular location at which you must put a facility. All right, so that's what you are doing in step 4. You place a facility, the kth one, xk. You define it to be the point on the edge segment TAT at which the end point of the shortest string reaches. Of course, you may have more than one shortest string, in which case, of course, they all reach the same point. Okay? You identify a particular vertex, which I denote by vertex with index not k, but rather parenthetical k. So that parenthetical k stands for a particular vertex whose definition is as follows. It's the vertex in the brown tree rooted at T, at which the shortest string the one whose endpoint has just determined the location of xk. So V parentheses k is the vertex in the brown tree rooted at the vertex T, at which the shortest string is originally fastened at. Okay? Initially, strings are fastened at vertices. Later on, they become engaged at vertices. So there's a difference between the two terms. Okay. And then we update the U set, the U sub k. We simply take the old one and add to it the vertex or the index of vertex V parentheses k. Okay? So k could be, for example, 3, which means you're placing the third facility. Parentheses k could be 5, which means that the third facility is defined, the location of the third facility is defined by a string that was originally fastened at vertex V5. Okay? All right. We then color T, XK, brown, and then we assign all pulled strings to XK and remove them. We then go to 5. Step 5. Assign to XK, the most recently located facility, all strings elsewhere in the tree and which reaches that point. So assign to XK all strings in G that reach XK. And delete such strings from further considerations, if they reach, of course. If they don't reach, you don't delete them. If no strings remain in the green tree, you go to the termination step, essentially. So if no strings remain, we let U to be the last version of UK, and then we stop. Else we go to 1. Step 6. This is the step that we came from number 1 in a special case. Okay. So in this case, there are the green tree was a singleton, and there were some strings attached. T attached means either engaged or originally fastened. So for that reason, you went to 6, and in that case, you still update K by 1, and then you put a final facility at that point. So in that case, what we do is we locate xk at t. We assign all strings that are present at t to xk. You delete them. Of these strings, we pick one of them. It doesn't matter which. You pick one, and you find the vertex at which this string was originally fastened, and you put that into the set UK. Then we go to 7. Let me just check one thing. Actually, let's add one more thing here. Put U equals UK, which is the last one, and stop. Okay, that's a termination step, and so we need to put that one. 7 is the step which you arrive at from a special case in step 1. There are no strings at T. In that case, we define, or let Q be the last value of K. I see. Okay, let me revise this because my notes are actually incorrectly stated. Okay, let's see. Why did I do it this way? Yeah, why don't you change that to go to 7? Because there's a mistake there. We don't stop, we go to stopping step is number 7. U equals UK and go to 7. And in this case, again, we go to 7. We just continue to 7. So please also revise that one. In step 7, you pick Q to be the last value of K. You define X to be the set of points you've located. And U is actually UQ, which we have already done actually in step 5 or 6, but it doesn't hurt to repeat it here, okay? Apparently when I was writing this down, I was in a hurry, and so there's a small revision needed in the wording, okay? All right, so you may notice that, let me just go through the algorithm in words. This is just the formal, well, it's a semi-formal statement of the algorithm. Of course, when you code this kind of stuff, you need to actually make it more understandable for computer to really follow what's going on, okay? But this is good for human minds. Nevertheless, it's instructions, a set of instructions to follow. So what you do is, you have a green tree. At the beginning, you fasten strings of appropriate length to each vertex. And then what you start doing is, you work from tip vertices towards inside. You pick one tip vertex, you pull the string tight towards the adjacent vertex. If the string does not reach, or let's take the case first, if it reaches. If it reaches, you simply color, you engage it there, and you color the portion between T and the adjacent vertex brown, and then you go back to repeat the procedure with the new situation. Okay? In the remaining case, it doesn't reach the string which is pulled tight. One of them, or the shortest one, does not reach at the beginning. Of course, there's only one. And so you just locate a facility at the very last point it reaches. Okay? And then you keep doing this. Meanwhile, as soon as you locate a facility, an xk, you identify a particular vertex at which the endpoint of the string, let me put it this way, you identify a vertex whose no, you identify a vertex at which the endpoint of the string is fastened at. And which string? The one that that determines the location of xk. So with that, you keep going, and we're going to make use of those vertices that we identify because they are somewhat critical vertices and they play an important role, actually. Okay? So we did an example on this. Let me just go through the example very quickly. I'm not going to go through the details, but this is what we had. Okay, that's the initial tree with the strings, with these lengths being attached at or fastened at the vertices. You've already got this in your notes. And we had a bunch of iterations. In the first iteration, I began with that one. And when you pull them tight, they both reached. So you browned, or you colored that section brown. And you have 4 and 7.2 here. Next, we happen to pick that one. There's a string, of course, of length 7 attached or fastened there. Okay, when you pick this, the length of this is 25, so obviously it won't reach the adjacent one. So you have to locate the first facility. When you locate it, your tree, your green tree becomes this one. This part is browned. There's an x1 here, and the length of this is 7, so the remaining length is 18. This was already browned, and now, as soon as I located x1, I checked all the strings, but none of them reached. So nothing is removed, okay, other than the one that came from here. So at this point, we of course identified the first U set. At the beginning, U0 was empty. So this is vertex 3. So my parenthetical 1 is 3. In other words, K is the iteration index. So that happens to be index 3 in this case. Okay? All right. Next, we chose that one as the tip vertex of the current green tree. And when you did it, you have an updating again. In this step, of course, we did not really do anything. Let me put my strings here. Other than just noticing that there are no strings, so you just color it brown. And that's one of the steps, actually. It's step 2. If there are no strings at T, color TAT brown and go to 1. Okay, so we executed that step. And now we choose V2 as a tip vertex of the green tree. When you do that, the shortest one, of course, reaches only so much. So you're going to have to locate a new point, which happens to be your x2 now. And that portion is colored brown. It has a length of 4. And U is also updated. It will become now U2, which has the first index 3 as well as the shortest strings vertex. What is the shortest strings vertex here? It comes from number 1. Okay? Of course, you have to do this on the side. There must be a mechanism to do some bookkeeping, but you can always do these things. So number 4 is your second critical vertex in this case. Okay? In the previous application of this algorithm last time, I did not really identify these UJ sets or UK sets, so please put them down now if you don't have them. Otherwise, later on, you may forget. Well, I guess you wouldn't, but it's better to have them down here. All right, the next one. Question? Sorry, 1. Yeah, it's 1. I guess I put down the length, the length of the string rather than the vertex index. Okay, so 3 and 1. And then the next one I happen to choose is V6, which is this one. Okay. Let me put my strings. This one is 8. This one is 6. This is 18. By the way, as soon as you locate that one, you should have checked these, but I guess none of them reach. Do they reach? No, they don't reach. Okay, so they remain in the green tree. So when you choose this, the length of this is 10, whereas the length of the string is 8. So you're going to have to locate one more now. That's going to be your x3. And so your U3 set will have 3, 1, and number 6. Does anybody else reach? That 6 reaches, so that one is removed. This one, that will not reach, so this still stays in the green tree. Okay? All right. So finally, we choose this one, which happens to be vertex number 5. When you choose it, you get your last one. Because it reaches only that much. And at this point, my U4 is 3, 1, 6, and 5. Now, at this point, all the strings are removed from the green tree, so we should be stopping. Did we state that somewhere? Okay, actually, we don't stop, I think, according to the way I stated the algorithm. So you're going to have to continue by choosing one of these tip vertices. When you do that, later on, if you happen to choose this one, for example, you will color that. And then you will choose that one, you will color that. This part is trivial, so I'm just doing it all at once. And then finally, you will color that portion. Finally, the green tree will be a singleton point, that point. At that time, step 1 will refer to, I guess, to step 7. At which time you stop, okay, with the correct solution. Okay, so here's the question now. Why do I know that the solution of the problem minimize cardinality of x subject to the distance between x and V1 is less than or equal to 12, dx V2 less than or equal to 7.2, dx V3 less than or equal to 7, dx V4 less than or equal to 6, dx V5 less than or equal to 18, and dx V6 less than or equal to 8, with x being a set of points in the tree that we have. Why is the solution of this cannot be any smaller than 4? That's the question we're raising. We did actually construct a feasible solution in the sense that the points that I located, they're always located to satisfy certain constraints of this form, distance constraints. And when you do that, if you find out that other strings also reach, then you also delete those constraints from further consideration. Deleting string means deleting a particular constraint, okay? So by construction, the set of points we found, the final set, consisting of x1, x2, x3, x4, is certainly feasible. There's no question about that, because strings are removed only if they reach some element of that set, which means all these constraints are satisfied. And the next question is, why should it be the case that this one cannot output any feasible solution with less number of points in it. So that's the question. And the example proof I'm looking for is actually, or should be proving, that statement that you cannot find anything smaller. Do you have a comment?
Yeah, I have an idea.
You have an idea. What is the idea?
We try to find a solution of less than 3 centers.
Less than 4, you mean?
Less than 4 centers.
Mm-hmm.
There should be another center between any two of these centers that will satisfy the complete solution. But
What do you mean? If I want to do the job with less than 4 points, then what do you mean? Then you need to have some point somewhere between. In other words, in the portion, in the convex, or well, in the portion that I colored brown last. Is that what you're referring to? Between x2, x4, x3? Hmm?
x2, x4, or x2, x3.
Between either x2, x4, or x... Okay. Why do you say that? You could be right, but I'm just asking why. What gives you the idea?
I should be able to find such a point. Otherwise, I know that these 4 points are the extreme points for some. For example, x1 is the extreme point for vertex 3, and x2 is the extreme point for vertex 1.
Mm-hmm.
So
Which one is which?
x1 is an extreme point for extreme center point for vertex 3, and x2 is an extreme center
for this one.
Yes, vertex 1.
Okay. So that one is a critical vertex. That's number 3. Okay.
And each of these points.
This one is V1. Mm-hmm. 6 is this one, and 5 is that one. Okay.
Each of these is an extreme point for a vertex. So it cannot be the new chosen center cannot be something between a vertex and, for example, vertex 5 and x4.
Okay, you have the right feeling, let me put it that way. But you're not really expressing it quite the way it's supposed to be. But you've got the right feeling. And of course, there's a reason why I wanted to deal with these special vertices. Obviously, they do play some critical role, except that you need to express that quite rigorously. I mean, that's a very special set of vertices, and we need to express that quite rigorously. So the claim is this particular problem, the example problem we have, cannot have any feasible solution that has less than 4 points in it. Less than means strictly less than, okay? It's not less than or equal to, but it's strictly less than. Okay, and I guess Hatice is suggesting that, well, that's so because we have four vertices here, the red ones, V1, V3, V5, V6, they are such vertices that just even if you just concentrate on those vertices, you're not going to be able to cover them all at the same time with 3 or fewer points. That's what you're trying to say, I guess. Forget the other ones, you're saying. These are enough to conclude or make the appropriate conclusion. NS, why do you think so?
Because I always some vertices with strings that not cover xi. That we can always find such a string.
Okay. So, consider the vertices in vertices whose indices are in U. U is what set? 3, 1, 6, 5. Vertices and vertex indices are the same as far as I'm concerned. So consider the vertices in U, 3, 1, 6, 5. When you look at those vertices, this one, well, let's just mark them here. This is V3, whose string length was 7. So that one is one particular one. This one is 12. And this one was 8. It was 8. And this one was 18. Okay, so V3, V1, V6, and V5. The lengths here are 25, 8, 22, 20, and 10. Now, when you look at these vertices, what do you see about them? For example, look at the distance between V1 and V3. How much is it? 8 plus 25. That's 33. How much are the string lengths? 7 and 12. So along this path, along the shortest path connecting them, if you just pulled those two strings tight towards each other, they would not connect. They would not reach. Which means that just for that pair, you cannot really jointly cover them, okay, by a single point. Well, consider the same situation for the pair V3 and V6. Again, 7 plus 18 is much smaller than the length of the shortest path connecting them. Okay, so they will not reach. Similarly so if you look at all these pairs, if you look at the distance between Vi and Vj as computed along the shortest path connecting Vi and Vj for the pairs 3, 1, 6, 5, so for Ij, both in set U, what do we know about them? We know that the string attached at A or fastened at A and the string length fastened at J, they will not reach, which means that the distance is greater than the sum of the string lengths. Okay? So that's what we have. Right, which means that so in other words, no two of these four vertices, no two of them can be jointly covered by a single point. Meaning that there does not exist any point x in the tree such that distance of x to vi and distance of x to vj, they are each less or equal the appropriate upper bound for pairs I and j both in that set. So the conclusion becomes obvious. Each such vertex requires at least one center by itself, because that center will not do the job for any of the other. Okay? Since you've got 4 such vertices, and since each one requires at least one point by itself, of course you're going to have to need at least 4 points in the feasible system. Okay? Let's take a break. That essentially gives you the important idea. After that, we can actually formalize that in a more general setting. Okay, let's take a 10-minute break, and then we'll continue.